Section 2.2, normal distributions. Normal distributions are density curves that are symmetric, single peaked, and bell-shaped. Okay, number one thing, do not start describing shapes of distributions as being normal. Remember, shapes are always symmetric, skew left, or skew right. A specific type of symmetric curve is a normal distribution that has to be also single peaked and bell-shaped. Okay, one standard deviation on a normal distribution is approximately halfway between the peak and the change in the curve of the distribution. In other words, as I look at this distribution here on the left, we can see that this is the mean plus one standard deviation right here. And you can see here's the peak. Right in here is where the curve starts changing. And halfway in between the peak and where that curve starts changing, approximately right here, is where the first standard deviation is. So it's going off to the left here. This would approximately be the mean minus the standard deviation. On this curve here, they've marked one standard deviation. Go halfway in between that peak, draw down, there's the mean minus one standard deviation. Two standard deviations on a normal distribution is approximately right after the change in the curve. So here's the change in the curve here. Right after that change starts, that's approximately where our second standard deviation is going to be. Is it imperative that you know exactly where these are? No, but it's nice when you are going to be drawing a lot of normal curves in here that you have an idea of what would be represented by the mean plus or minus one standard deviation or two standard deviations. Reviewing the empirical rule, we talked about this in section 2.1. 68% of the observations fall within one standard deviation of the mean. 95% of the observations fall within two standard deviations of the mean, and 99.7% of the observations fall within three standard deviations of the mean. Remember, the empirical rule only applies to symmetrical distributions. Graphically, same thing that we talked about in section 2.1. Make sure that you understand how that graph applies to what it is that you are doing. Notice the numbers down here are just simply how many standard deviations above the mean or below the mean we are talking about for each group of data. Problem 24. The distribution of heights of adult American men is approximately normal with a mean of 69 inches and a standard deviation of 2.5 inches. Draw a normal curve on which this mean and standard deviations are correctly located, and it gives you a hint to draw the curve first, locate the points where the curvature changes, then mark the horizontal axis. Okay, so we're going to go ahead here and draw our normal distribution. Again, you are sketching this. It's not going to be 100% accurate. So draw as good of a curve as you can. That's obviously symmetrical and bell-shaped. We know at the peak is going to be our mean, which in this case is 69. Should label this axis height. And how are we measuring the height? In inches. Let's go out one standard deviation first. Okay, one standard deviation on either side. You should be moving the same distance approximately left and right. 2.5 inches, take 69 plus 2.5. That's 71.5. There's one standard deviation. Subtract 2.5. 66.5, there's one standard deviation below. So this is the mean. This is the mean plus a standard deviation. This is the mean minus a standard deviation. Add one more standard deviation. So now this is the mean plus 2 standard deviations. This is the mean minus 2 standard deviations. And finally go out to the third, 76.5 and 61.5, measuring the mean minus 3 standard deviations and the mean plus 3 standard deviations. So there's what our curve would look like. Problem 26. The distributions of the weights of 9-ounce bags of a particular brand of potato chips is approximately normal with a mean of 9.12 ounces and a standard deviation of 0.15 ounces. Draw an accurate sketch of the distribution of potato chip bag weights. Be sure to label the mean as well as the points 1, 2, and 3 standard deviations away from the mean on the horizontal axis. So we're going to do the same thing that we just did on the previous example, but now for these weights of potato chips. So draw your curve again. This time we are measuring weight in ounces. Mean weight is 9 ounces. Okay, and notice here, and this is how things work in the real world. When you go buy a bag of potato chips, it says on the bag that it weighs 9 ounces. Does that mean every single bag is filled with exactly 9 ounces? No. When you go buy a gallon of milk, does it mean that every single jug of milk is filled with exactly 1 gallon of milk? No. So, because there's variation, and there's variation in the real world. The distribution in this case of 9-ounce bags, it says the mean is 9.12. So this company is purposely overfilling most of these bags. Why are they doing that? Because they don't want the consumers to get irritated that, hey, I paid for a 9-ounce bag of potato chips and there's less than 9 ounces in here. Okay, so notice that they're purposely overfilling. It doesn't mean that some of them still aren't going to be under 9 ounces, okay, as we're going to see here from the distribution. So if we go out 1 standard deviation, our mean was not at 9. Sorry about that. It was at 9.12 ounces. Mean plus a standard deviation. And the mean minus a standard deviation. Mean plus a standard deviation puts us at 9.27 ounces. Mean minus the standard deviation puts us at 8.97 ounces. Go out 2 standard deviations. So add 0.15 again, we're at 9.42. Subtract a standard deviation, and we are at 8.82. Go 3 standard deviations, and we are going to be at 9.57 and 8.67. Okay, so there's our distribution. Now we're going to use this distribution to answer some questions. First one, a bag that weighs 8.97 ounces is at what percentile in this distribution? Well, we're told here that our distribution is approximately normal, meaning we're dealing with a symmetric shape. Okay, what things do we know here based on the empirical rule? Well, a couple things. First of all, remember that to the right here is going to be 50% of our data. To the left is going to be 50% of our data. Within 1 standard deviation is 68%. So between here and here is 68% of our bags of potato chips weighing between 8.97 ounces and 9.27 ounces. Likewise, we can say, well, if there's 68% in there, that means there's 34% in this section, 34% in this section. So now the question was, how many, or a bag that weighs 8.97 ounces is in what percentile? Well, here's 8.97 ounces. Percentile means how many bags are at that value or less than that value. Well, in order to help us do that, we can figure out how many are to the right of it pretty easily. Okay, we know from the mean right here, over is 50%. We know between here and here is another 34%. So that means 84% of the bags weigh more than 8.97 ounces, which means 16% then have to weigh less than. So that means we are talking about the 16th percentile. What percent of 9-ounce bags of this brand of potato chips weighed between 8.67 and 9.27 ounces? Between 8.67 and 9.27. So we're talking about from here to here. All right. So what do we need to do here to figure that out? Well, there's a couple of different things we can do. We know that if we use the empirical rule, 95% are between 2 standard deviations. So from here to here, remember this is the 99.7%. So this from here to here is about 50%, because remember outside of 3 standard deviations isn't much. 34% in here, so it's about 50% plus 34%, a little bit less than that. But again, we're estimating here, so we can say about 84% of the bags are between 8.67 and 9.27 ounces. Standard normal distribution is the normal distribution given by n of 0, 1, with mean 0 and standard deviation 1. This notation is notation that you will see for a bunch of different types of distributions we're going to talk about. The n tells you that the distribution is normal. The 0 tells you that the mean is equal to 0. And the 1 tells you that the standard deviation is equal to 1. Okay, so you see this abbreviation N and then in parentheses 0, 1. That's telling you the type of distribution, normal. First number is the mean. Second number is the standard deviation. Those are the two things that you must identify anytime you are talking about a normal distribution. If it's normal distribution, identify mean and standard deviation. Okay, just like shape is symmetric, we use mean and standard deviation. Since normal is a symmetric distribution, we're going to identify it by those two important characteristics. If a variable x has any normal distribution given by mu and sigma, with mean mu and standard deviation sigma, then the standardized variable we already talked about is x minus the mean divided by the standard deviation. Table A is a table of areas under the standard normal curve. The table entry for each value z is the area under the curve to the left of z. Okay, we're going to both be using our Z tables from the book or the handouts that you were given, as well as using them finding with the calculator, and we will be talking about both. So looking at problem 30 here, use table A to find the proportion of observations from a standard normal distribution that satisfies each of the following elements. In each case, sketch a standard normal curve and shade the area under the curve that is the answer to the question. Okay, whenever you are working with a normal distribution, it is always a good idea to draw a picture of what it is you are finding. On the AP exam, on quizzes, tests, and here, the picture shows a deeper understanding of things. So sometimes if you are between points and you have a good picture drawn and it shows a better understanding, you may get 3 out of 4 points rather than 2 out of 4 points, and so on. So the first one here, z is less than negative 2.46. Again, your sketch doesn't have to be anything very detailed. Simply draw a quick normal curve. We know in the middle is always our mean. Label this what it is. This is a z-score along the bottom here. And we know negative 2.46 is going to be, well, out to the left. So if we want to know the probability, or I'm sorry, z is less than negative 2.46, and you are finding that area right there. And I already almost slipped and said probability. This is going to be linked to probability later on. Right now we're talking only in terms of area under the curve, so we're looking for that area to the left there. So we're going to do this two ways. Let's first look at our chart. If we look at our chart, negative 2.46, we're going to take this at negative 2.4, follow it all the way over to the 0.06 column, which is going to be that value right there, 0.0069. So back on our page here, we know that z is less than negative 2.46, has an area of 0.0069. On the calculator, if you go into your distribution menu, maybe, let's see what's going on here. Okay, there we go. Hit second function. And then your vars key, which is to get into your distribution menu. And you see normal CDF there. Normal CDF stands for normal cumulative distribution function, so select that. And now you need to give that two commands in your calculator. You need to tell the left bound, how far left are we going? Well, it goes out to infinity to the left, okay? But when we're talking in terms of a normal distribution, and this is going to work for all the distributions you're talking about, go out to negative 100 and up to positive 100 if you were talking an area to the right. So you set your left bound and your right bound, which is the negative 2.46. Hit enter. And there's the same value that you got from the table. Okay, so on the calculator, and I'll write the calculator stuff up here in green. Normal CDF from negative 100 to negative 2.46. Okay, on quizzes, tests, AP exam, do not write this calculator stuff up there. They don't care about that. That's not going to help you get any points. Letter B, z is greater than positive 2.46. Again, draw a sketch of the distribution. There's our mean in the middle. 2.46 is going to be somewhere out here. We're finding that area. Without even going to the chart, knowing that this is a symmetric distribution, that area better be equal to what? Yeah, it better be equal to 0.0069. Let's verify both on the chart and calculator. On our table first, we need to go to our positive z-score values. So I'm going to go up a page here. We're looking at 2.46, 2.4, follow it over to the 0.6 column. We get that value right there, 0.9931. Remember, that's telling you the area to the left. We know the area underneath any density curve, which the normal distribution is a density curve, is equal to 1. So if I wanted or had to calculate this by hand, I would have to take 1 minus 0.9931, which is 0.0069. On the calculator, most of you are probably going to use the calculator for most of these calculations. Again, we would go normal CDF. Our left bound is positive 2.46. Our right bound, we're going all the way out to 100. And there is the value. Letter C. .89. up to 2.46. We're looking for that area right there. Let's take a look at that on the calculator. Normal CDF from 0.89 up to 2.46. We get 0.1798, and everything is going to be rounded to 4 decimal places here when we talk about this area. And now that I look at this, I put the 0.89 on the wrong side, so let's redraw that. So there's our mean. 0.89 is going to be somewhere here. 2.46 somewhere out here. So we're looking for that area right there. When we plug that into the calculator, we got 0.1798. Let's take a look at how we would have to do this if we didn't have the calculator. So very quickly, this is the last one that we will look at the table. Okay, to find the table, remember it's giving us the area to the left. So we know the area to the left of 2.4 is 0.9931. The area to the left of 0.89, let's take a look at that. 0.89 is right here. So what I would need to do is take that value that we had for 2.46 and subtract that to find the area in between. So that's going to be 0.9931. Minus 0.8193. Okay, the last one here. Again, draw your normal distribution. Mean in the middle, negative 2.95 and negative 1.27. So we're talking about this area in here. Easiest done on the calculator. Go ahead and plug that in. Normal CDF, second function distribution. Number 2, normal CDF from negative 2.95 up to negative 1.27. Round to 4 decimal places, 0.1005. Solving problems involving normal distribution. Step 1, state the problem in terms of the observed variable x. Draw a picture of the distribution and shade the area of interest under the curve. Okay, so that's what we did right here, where we drew our pictures. Number 2, standardize and draw a picture. Standardize x to restate the problem in terms of a standard normal variable z. Draw a picture to show the area of interest under the standard normal curve. Use the table. Okay, you can also use a calculator and write your conclusion in the context of the problem. Okay, this right here is going to be important to everything you do all year long. Anytime you are answering a question, do so in the context of the problem, not in general terms. Use Table A to find the value z from a standard normal distribution that satisfies each of the following conditions. Use the value of z from Table A that comes closest to satisfying the condition. In each case, sketch a standard normal curve with your value of z marked on the axis. Use the normal curve applet to check your answers. We don't need to do that. We're going to use the calculator as well as the table. The point z with 25% of the observations falling to the left of it. So again, if I drew a picture of what's going on here, draw your normal curve. From your normal curve here, we want to know what value of z down here is going to be so that this area right here represents 25% of our data. two different ways we can do that. Let's first go to the chart. From our chart now, we're looking for an area of 0.25. We know that occurs at a negative z-value. So let's go back up to our negative z-values. We're looking in the body now because we're talking about the area. We're looking for 0.25. So go through these areas looking for 0.25 is closest to right here. What z-score matches up with that? That's negative 0.67 if we trace that up. On the calculator, and I'll write this in blue. You would put in inverse norm of 0.25. In other words, you're using your normal distribution in the opposite direction. So go to your calculator, into your distribution menu again. You see inverse norm is number 3, inverse norm 0.25. And you see there's your z-score. Z-scores round to 2 places, areas round to 4 decimal places. Letter B, the point Z with 40% of the observations falling to the right of it. Okay, 40% to the right means that 60% needs to be to the left. And remember, that's how we calculate it in the calculator. Okay, let's first look on the chart again. So now we're looking for an area of 0.6. We know that that has to be a positive z-value, so let's go to the positive chart. We're looking for an area of 0.6. We can see the closest one to that is right here, which is 0.25. On the calculator, we would simply go inverse norm. So in your distribution menu, inverse norm of 0.6, hit enter, and we get 0.25 there as well. So again, couple things in general. Round z-scores to 2 decimal places. Round areas to 4 decimal places. Problem 34. Scores on the Wechsler Adult Intelligence Scale, a standard IQ test for the 20 to 34 age group, are approximately normally distributed with a mean of 110 and a standard deviation of 25. For each part that follows, sketch and shade the appropriate normal distribution, then show your work. What percent of people aged 20 to 34 have IQ scores above 100? Okay, so we're going to have 2 scales here. We're going to have one in terms of X. I'm going to have a second scale down here in terms of our z-score. First of all, we know the mean is at 110. The mean correlates to a z-score of 0. 0 standard deviations away from the mean. We're told that the standard deviation is 25. We want to know how many or what percent of the people have scores above 100. So there's 100, and we would be looking for that area to the right. In order to do that, we need to find the standardized value of that score. Find your z-score. 100 minus 110 divided by 25 gives you a z-score of negative 0.4. So that's the value right down here. And now we're finding the area to the right of that z-score. So we want to know z is greater than negative 0.4. It's the same thing then that we would have to find by taking 1 minus the z-score being less than negative 0.4. So that's how we would plug it in if we were doing it on the table. We don't need to do this on the table. We can find it directly on the calculator. So now that we know our left bound is 0.4, our right bound is 100, we can go normal CDF from negative 0.4 up to 100. We get 0.6554. So that means that 65.54% of adults age 20 to 34 have IQ scores higher than 100. Part B, what percent have scores above 150? So again, we're going to set up our table. 150 is out here. We need to find the correlating z-score for that, which is going to be 150 minus 110 divided by 25, and we get the z-score to be 1.6. So again, we want to know greater than that, so we're looking for that area right in there. Standard deviation you should always identify, which was 25. And now we're looking for the area to the right of 1.6 on our z-table. Go to the calculator. Normal CDF from 1.6 up to 100. It's an area of 0.0548. Which means that 5.48% of adults 20 to 34 have an IQ score higher than 150. Letter C, Mensa is an elite organization that admits as members people who score in the top 2% on the IQ test. What score on the intelligence scale would an individual have to earn to qualify for Mensa membership? Okay, once again, draw your distribution. There's our mean score of 110. We're looking for the top 2%. So we're talking about this small area right out here. We're looking for that score. Well, we can find the z-score corresponding to that because we know that if there is 0.02 in here, that means that there is 0.98 in this area to the left of that. So if you use your calculator, you're going to go inverse norm because you're looking now for the z-score. So into your distribution menu, inverse norm of 0.98 corresponds to a z-score of 2.05. And now we can use our z-score formula backwards to find the score that is going to produce that. So using our formula here, z-score 2.05 equals the x value which we're looking for minus the mean divided by the standard deviation. Plug that into your calculator, solve for x. Should get x to be 161.25. That's this value right here. So that means that adults must score above 161.25 to be admitted to Mensa. The amount of time Ricardo spends brushing his teeth follows a normal distribution with unknown mean and standard deviation. Ricardo spends less than 1 minute brushing his teeth about 40% of the time. He spends more than 2 minutes brushing his teeth 20% of the time. Use this information to determine the mean and standard deviation of the distribution. So we know it follows a normal distribution, so let's start by drawing our normal curve. Okay, so we know the mean still has to be here in the middle, but we don't know what it is. We know that he spends less than 1 minute brushing his teeth 40% of the time. So if 1 minute was out here, we know that that area right there is going to be 0.4. And he spends more than 2 minutes, 2% of the time. So that area is 0.02. If we convert those to z values, first z value, inverse norm of 0.4 will give us this one. Inverse norm of 0.98 would give us this one. Let's go to the calculator and find each of those. Calculate inverse norm of 0.4 and inverse norm of 0.98. So we have negative 0.2533 and 2.0537. Go ahead and label those on our picture here. Remember, z-scores to 2 decimal places, so 2.05 and negative 25. And now we want to know or determine what our mean and standard deviation are. Well, let's take this first z-score right here. This z-score, negative 0.25, equals the x value, which is 1, minus the mean divided by the standard deviation. For the second z value, 2.05 equals 2 minus our mean divided by our standard deviation. And now we have a system of 2 equations, 2 unknowns. If I multiply by sigma, we get negative 0.25 sigma equals 1 minus mu. And here we get 2.05 sigma equals 2 minus mu. You can use substitution or elimination to solve this system. I am going to use elimination. Multiply this equation by negative 1, move it down to here, add those up. We get negative 2.3 times sigma equals negative 1. So our standard deviation is going to be 0.4348. Once we know standard deviation, we can plug into either one of these to find what mu is. Mu is going to be, when we plug that in, 1.1087. So what do we know about this distribution now? We know it is normal with a mean of 1.1087 and a standard deviation of 0.4348. There's how we would describe the distribution. Last thing in this section is assessing normality. Histogram in figure 2.3 suggests that the distribution of 947 Gary vocabulary scores is close to normal. It is hard to assess by eye how close to normal a histogram is. If we use our empirical rule to check more closely, we enter the scores into a statistical software package and ask for the mean and standard deviation. The computer gives us that mean and that standard deviation. Now that we know those two things, we can check the empirical rule by finding the actual counts of Gary vocabulary scores in intervals of length s about the mean x bar. So there are our counts. We can see from those counts that it does appear to be a normal distribution. It's very close to symmetric. It also follows the empirical rule closely. 68.5% are within one standard deviation, 95.4% are within two, and 99.8% are within three standard deviations. So we can see that that's very close to a normal distribution. Normal probability plot is what you are going to use most of the time to assess normality. If the points on a normal probability plot lie close to a straight line, the plot indicates that the data are normal. Systematic deviations from the straight line indicate a non-normal distribution. Outliers appear as points that are far away from the overall pattern of the plot. So let's go to page 54 in your book, example 1.8, and let's enter those values into the calculator. Okay, so there's the table. Enter those 23 values into your calculator. Once you enter those 23 in, then we are going to go ahead and assess the normality of this distribution. I've already entered them in here. So I'm going to go into my stat plot menu. Actually, I'm going to go into y equals first. Make sure you don't have any other equations in there. Select plot 1 to turn it on. Go into your stat plot. And now on your stat plot menu, the very last graph here that we didn't talk about is your normal quantile plot. Hit enter on that. Okay, from there we want it to pull from list 1, assuming that that's where you put them in at. Go zoom stat, which is zoom 8 on here. Sorry, it's zoom 9 on this one. Okay, there's our normal quantile plot or normal probability plot. And again, what the normal probability plot is doing is converting each one. Let's change our scale here so we can spread this out a little bit more. Let's go by 500s. Just doing this to get a little bit better picture for you here. Okay, there's our graph. We can see that this is very, very close to a straight line that all these points lie on. Okay, so we could say from this graph that indeed this is going to be approximated by a normal distribution. There's a graph of the same thing we just saw in our calculator. Straight line relationship, so we could say that that is approximated. Next one, use the given probability plot to decide whether this distribution is normal. Is this a straight line relationship? No. So you would say that this is not a normal distribution. This one here very clearly looks like a linear relationship. So you would say that this is a normal distribution. Okay, notice what a normal probability plot is doing is it's taking all of the values and it's converting them into, or converting the x-axis into the z-score corresponding to that value. So that's what your calculator is doing for you. You're not going to have to ever do that by hand. You have that normal quantile plot or normal probability plot, which you can use at any time to assess normality of a distribution. Okay, looking very quickly here. Again, I'm not going to go through all of this. A couple things I want to remind you for calculator. To find the area between two z-scores, remember on the calculator, that's your normal CDF. And you also can go in reverse and go inverse norm. An inverse norm is for finding the z-score given an area. The rest of that, read through, make sure you know the boldface terms. If there's conceptual things you have questions on, make sure that you see me.